Okay, we are on the last section. Kinematic equations derived from calculus. So let's bring this up. I think, was there? All right, kinematic equations derived from calculus. If we have a varying velocity, as shown here, the area of the shaded, uh, we have a velocity curve here, and it's not constant, and the acceleration obviously is not, doesn't appear to be constant either. We can look at the area under the curve, but how do we get the area under the curve? Well, we divide up into these individual rectangles. So from t initial to t final, we come up with a small delta tn, and we come up with the area under that section, under that rectangle. And if you'll see that the top of the little rectangle is right at the midpoint of the curve. If we add up all of those rectangles, we get an approximation of the area under the curve. And if we start adding more and more intervals, the delta Tn gets smaller and smaller and smaller. So we can define a limit. Let's look at here. X sub n is equal to Vx sub n average times t. So the V times t gives you the displacement for that particular interval. Delta x is equal to the first one was talking about just the x sub n, the displacement for that little section. Here, the total delta x is equal to the sum of all these Vxn average times delta Tn. And if we look at the limit, x is equal to the limit as delta n approaches 0. That is, as n increases, it's the sum of all of these Vxn averages times the delta Tn. And if you calculate all of those, you get the area under the curve. So in calculus, this is known as an integral. Some people call it an antiderivative. I just call it an integral. The delta x is equal to the integral from evaluated from t initial to t final of Vx t dt. So this is the integral to give us the area under the curve, which will give us delta x. Now, by the same token, we can look at ax is equal to the first derivative of velocity. So dvx is equal to ax dt. So the initial velocity minus the final velocity minus the initial velocity is the integral from 0, assuming that t initial is 0 to t of ax dt. Well, if the acceleration is constant, as we've been talking about in this particular chapter, a constant acceleration, you can pull the acceleration out in front of the integral sign. So Vx final minus Vx initial is equal to the acceleration in the x direction integrated times the integral evaluated from 0 to t of dt, which is just t. So it's axt, and evaluated from 0 to t, it's t minus 0. You get axt. And if we solve for, well, they don't show it here, but if you, it's Vx final equals Vx initial plus axt, and that's what we had in one of our equations. So that's a familiar equation. Now let's look at Vx is equal to dx dt, so dx equals Vx dt, and x initial, x final minus x initial is equal to the integral of 0 to t of Vx dt. Vx is equal to Vx final equals Vxi plus at. That's the result at that bottom equation. Vx final equals Vx initial plus at. Now x, if we take the integral of that right-hand side, integral evaluated from 0 to t of Vxi plus axt dt, well, we have to break that up into parts. So it's integral of Vxi dt plus ax, assuming constant velocity, ax times the integral of 0 to t times t dt. Well, if you take the integral, that's just integral of dt is t, evaluated from 0 to t is Vxi times t minus 0, and plus ax, well, the integral of t dt is t squared over 2, which gives us our familiar x final minus x initial equals Vxit plus 1/2 axt squared. We're used to seeing it as x final equals x initial plus Vxit plus 1/2 at squared. And that's the end. That's getting the kinematic equations getting derived from calculus. And we'll stop sharing and stop the recording.